best way to use our laptop to diminish the risks.
Okay. Donc c'est dès qu'on branche quelque chose d'autre.
J'ai pas encore trouvé la.
Ok, t'as pas encore trouvé la source, mais quand tu le mets là,
mais non, mais c'est pas d'ici, c'est
l'installation en elle-même.
C'est des ouais.
Ok. Bon, bah on attend plus que la présentation arrive sur le drive.
Ok.
Et on commence. Avec ma laptop.
All right.
Sorry.
Thanks for bearing with the technical difficulties. My name is Chadwick Strange. I'm VP of Product at Scale Labs. I'm presenting on how to build effective trustless networks on Ethereum. Let me just ask, who here has heard of Scale Network? Okay, cool, awesome, great. So I wanted to conceptualize this interview as, or this presentation as, we have a challenge here. Let's say that we need to build an effective layer 2 proof of stake network to scale Ethereum. And it has to be 100% compatible coupled with Ethereum, because how can you use a scaling solution if you're using Ethereum and need to learn an entire other technology ecosystem? So there must be that tight coupling. This network must be self-regulating and self-reinforcing. To be decentralized, all the actors need to sort of check one another, and all the scaling resources must be commoditized in an efficient way on a market, such that any dApp developer or someone who needs a scaling technology can do so at any given time with efficient prices and get those resources from the network easily. And the network agents may be Byzantine at any given time, meaning these agents might go down, they might be inactive, or they might refuse to communicate with the network. So any sort of Byzantine type of behavior on the network. And the entire network setup must be trustless and decentralized. So this is quite a tall order for a design and technical specification. And this is exactly what Scale Network does. And this all does from a particular way of how we architected the network. And in talking to a lot of people about Scale Network, I've seen a lot of confusion about this. And I wanted to create this presentation to sort of guide people through this sort of nuance, but really important part of how our network is structured. And that has to deal with the Scale Manager system. And the Scale Manager system is a set of Ethereum smart contracts that is designed and is deployed onto the Ethereum network. And this Scale Manager, this set of contracts, it actually orchestrates all the business, all the functional logic to empower this layer 2 proof of stake network. So it lives on Ethereum, it's tightly coupled with Ethereum, uses all the great security mechanisms of Ethereum, being decentralized and a proof of work layer 1 mechanism. And this contract basically orchestrates all these nodes, all these hexagonal nodes of computing power that is providing this power to this layer 2 proof of stake network. And because it's built on Ethereum using Solidity contracts, it's compatible with Ethereum. It's compatible with Ethereum when you deploy onto a scale chain. It's also compatible with Ethereum in that the entire business is compatible with Ethereum. And it's tightly coupled to the Ethereum network because we don't want people to know that they're on a completely other network to get scaling technology. It must be tightly coupled so that you don't even know that you're using an entire other network to scale your decentralized applications. And part of how we provide the power to the network is through a function of the Scale Manager system that deals with validator and delegator flows. The Scale Network is a proof of stake network, so any agent or any business can come and create a validator business onto the network and then register nodes onto the Scale Manager, which they're communicating with the contract on Ethereum, and accept delegation and staking, and all these flows are defined in functions in the Scale Manager contract, such that the Ethereum mainnet is used as an anchor point to orchestrate the registration of validator nodes, to orchestrate the delegation of delegees into the network, into the Scale network of validators, and to provide resources from these computing resources that validators are providing. On the right here, I have an example. This sort of rectangular box is a representation of a single validator node. So a validator can register onto the network. They can accept delegation up to the minimum staking requirement. And this allows them to operate a node on the Scale network. And this is all, again, done through interacting with a scale manager contract on Ethereum. And a validator can have any number of nodes so long as those delegations that he or she receives meets the minimum staking requirement cumulatively across all the nodes. This function is also done in the scale manager system such that it's a pretty simple flow. You register as a validator, you register the number of nodes, you accept delegations up to the MSR requirement for the number of nodes that you have, and then those nodes become registered with the scale manager and become operative on the scale network. There are some other proof-of-stake network systems where the payment of bounty payments is put on the onus of a validator to handle. For the scale manager system, we've actually coded that in as a calculative operation, that all the bounty payments are also done on-chain in a transparent manner, such that if you're a delegator, at the end of every epoch, your rewards that the validator and the delegators earn are automatically divvied out to all the validators and delegators. And then all the slashing conditions are also orchestrated by the scale manager system to keep people compliant and complete them, incentivize them for good behavior. And again, all the slashing is done through on-chain contracts, and so all of that process is transparent. Another part of the network, given that you have validator nodes that are operating, you have many agents or many validators operating these validator nodes, how do we make sure all these validator nodes are operating well, they're operating very performant, and these validators are operating them with good infrastructure? We need to have a monitoring mechanism for every single validator node in the network to then monitor or self-police every other node in the network. And that could be across other validators or whatnot. So we created this concept, again, in Scale Manager, where every node is monitoring every other node. The network is actively self-monitoring, self-reinforcing. So over the given epoch of a certain month of operation, for all these validator nodes to exist on the network, every single node is monitoring 24 other nodes and reporting that information to the scale manager system on Ethereum. And so what this looks like is when you register a validator node on the network, you're interacting with the scale manager system. Scale manager generates a random group of 24 nodes that your node is responsible for monitoring. And your node will automatically find those groups and then start measuring automatically over the given month and reporting statistics of like uptime, the performance, and reporting that to the scale manager as a verdict at the end of the epoch. And this verdict is used to help ensure that bounty payments are accurate. So at the end of the month, if you're a performant node, the majority of the network is a performant node, all network operators will earn their optimal bounty. If you're a node that tends to be offline like half the time or have very unperformant metrics, and you're way outside the tolerance interval or an outlier, you might be paid a little bit less than your optimal bounty payment for the month. So again, this system is all recorded onto the scale manager system on Ethereum. The other thing about the network, so we've talked about validator nodes and how they can provide resources to the network. We've talked about how all these nodes will monitor every other node of the network. A scale manager system also monitors the resourcing of scale chains that come out of these validator nodes that are provided for dApp developers to scale their applications. And so this resourcing, we've created an efficient market for scalable resources that's actively monitored and allocated out by the scale manager system. So we have this commoditization of resources and a market for scaling. And how this is done, is the scale manager tracks the resourcing available in every single node. And so if a fraction of the node resource is given for a scale chain, the scale manager system checks that to understand the health or whether the network is at capacity, and then regulates whether to incentivize more validators to create more nodes to then balance the supply and demand of the network. When a scale chain is created, a group of random nodes is selected by the scale manager to provide resourcing for that particular scale chain. As well, the scale manager also, you can think of these hexagonals or circles as each scale chain. And so these are individual nodes that participate in a scale chain. And over time, scale manager swaps these nodes out at random. The reason for this is a single scale chain could operate a smaller dApp. It could operate a huge dApp, like say a decentralized exchange with quite a bit of assets on top of it. Over time, you could actually have a collusive behavior where you can learn all the other nodes of your network that's also operating that decentralized exchange. To prevent collusion, we swap nodes randomly out of the scale chain and swap a node in. And so there's this node rotation procedure that is seamless for the dApp developer. You don't really know that that node rotation is happening. But again, that's all done by the scale manager system to prevent collusive behavior over time. Let me just ask, before I get there, so I'm a product guy, I'm not a mathematician, I'm not a cryptographer, but I want to ask, what cool crypto algorithms does the audience know of or is aware of? Just curious. Okay. NuCypher, okay. Well, one of my favorite crypto algorithms that I got into in terms of product was the joint Feldman protocol. The reason for this is our entire scale network uses threshold cryptography. And for threshold cryptography to work, we use BLS threshold signatures. BLS threshold signatures is a really great technology. The only difficulty in implementing BLS threshold signatures is actually doing a ceremony called distributed key generation. We use the joint Feldman protocol for distributed key generation. And that's because this threshold crypto system using DKG and BLS threshold signatures becomes very powerful coupling for Byzantine fault tolerant state machines. If you're operating a scale chain and a number of nodes are Byzantine, how can you then facilitate signing blocks without having a threshold crypto system? With a threshold crypto system, nodes can be Byzantine, they can be offline, but up to a threshold of nodes can continue to do signing operations with BLS threshold signatures. And so Scale Manager System also has this on on-chain contracts. We have elliptic curve Diffie-Hellman key exchange, BLS threshold signature verification, and distributed key generation contracts that are on our Scale Manager System that also facilitate network operations. And the goal for this crypto system function is that every node that participates in a scale chain should have its own private key. And then all nodes that are on that scale chain combined should have a shared public key to sign blocks onto their blockchain. Nodes can be Byzantine, they can be offline or refuse to communicate with the network. But up to a threshold, they can still perform signing operations with these threshold signatures. And the signature is the same regardless of any combination of signers. So you can have 12 signers, 13 signers, the signature is still the same. It's pretty magical for BLS threshold signatures to do that. And this entire setup to create these private keys and public keys must be done without any trusted partner. So the next couple slides, I spent some time to try to conceptualize what this protocol is doing because I think it's pretty elegant. So I kind of went crazy on animations and PowerPoint, so hopefully this won't work. Or hopefully this will work. On the left, which you don't see right now, well, you don't see it because of the screen, but there are 16 triangles here, and each triangle has a key. Each of these keys right here are representing public keys from other nodes. So what happens in DKG process to begin this, every node is creating a disposable key, and every node has its private key, and so there's a swapping or exchange. So one node will take its disposable key and take all the other public keys of all the other nodes, and it will sign or encrypt, or rather encrypt its own disposable key. And so you would generate 240 of these encrypted disposable keys using every other node's private or public key. And this information is sent over to Scale Manager System on Ethereum. To simplify the animations, I cut down all 240 keys to basically, let's say there's an encrypted, encrypted key with the other 15 public keys. What also happens is the nodes send something called a verification vector to the scale manager system. And now what happens is that each node will download from the scale manager this verification vector from other nodes and the encrypted disposable key. And every node will check every other node to see what, using the verification vector and this key, of whether they match. And if there's a match, every other node is doing this iterating over all the keys, the encrypted keys. So they check and they match, everything looks good. The scale chain will send an all right message to the scale manager system. And then what happens is a broadcast method where there's a broadcast of the summary of the verification vectors over to the scale chain system. And this is done 16 times. And after this is all received, after 16 times, each single node uses this information to then generate its own private key. And the cumulative final summary of the verification vector is the common public key. So this allows every single node to sign a block up to a certain threshold. Now you might ask, what happens if this process occurs and that there's an issue? So maybe one node was trying to be malicious, so they sent bad information. So node 16 at the bottom here picks out an incorrect match. The node system will then send a complaint to the scale manager system. At this point, the DKG process has failed and will begin to restart with a new group of nodes to create this scale chain. But we still need to figure out whether that complaint was valid or not. So the next process is that node 1 must send its disposable key to the scale manager to prove whether they are in violation of this complaint. So that's sent to the scale manager. There's a check that ensues, and if the disposable key does not match, that node then becomes slashed. If the node refuses to send its disposable key in a certain amount of time, it is also slashed. If that disposable key actually matches, then the complainer will be at fault for submitting erroneous claim. So what I've gone through are some key features of the scale manager system. Again, we've made it to be tightly coupled with the Ethereum network by deploying these contracts onto Ethereum. This has allowed us to basically orchestrate our entire network, or our layer 2 proof of stake network, to help Ethereum scale today. And this allows validators and delegators to interact with the scale manager system to provide computing power to the network. The network is self-regulating. Scaling resources are commoditized in an efficient way and all tracked by the scale manager system. Network agents may be Byzantine, and this is all orchestrated in a trustless, decentralized, and open source manner using scale manager system on Ethereum. You can check out our website at scalenetwork.com. We also have our GitHub where all this code is open sourced. So feel free to take a look at the technology and use it as you wish. I'm Chadwick Strange. I'll be happy to take any questions. Thank you.
If we could take questions outside the room, because we're obviously running a bit late. So we're sorry we have to move.
Thank you.
Thank you.